We're in the demo lab with Lonnie to see a controlled explosion. Lonnie's going to react carbon disulfide and NO gas. The reaction releases a tremendous amount of energy, 3,000 kilojoules per mole. But the kinetics is such that the reaction actually occurs relatively slowly. It's a complex chemical reaction involving many steps. Lonnie's going to mix the two chemicals in this giant test tube. Now, the reactants have to be mixed very thoroughly. So we'll see Lonnie mix this by inversion. The reactants have to be thoroughly mixed because we need all the chemicals to react together. So we need all the chemicals in proximity to each other and have a thorough mixture for the reaction to proceed to completion. Once the chemicals are mixed, Lonnie can initiate the reaction with a flame, and a slow explosion will proceed down the length of the tube with the emission of a brilliant blue light and an interesting sound. That's the reaction of carbon disulfide and NO gas. One way to determine the energy content of food is to do a calorimetry experiment. You can burn the food in oxygen, just like it's consumed in your body, and measure the heat output in joules, or in calories, the more common nutritional unit of energy. So here Lonnie's preparing to burn a donut in liquid oxygen. Now, this isn't a formal calorimetry experiment because we won't capture all the heat released, but we'll just visually demonstrate the amount of energy stored in a bite of donut. So to start this reaction, Lonnie will start the donut burning in oxygen and then add it to the liquid oxygen so it rapidly combusts and we'll see the energy released rapidly. So Lonnie takes the donut and he begins the combustion, releasing a small amount of the energy now as the donut begins to burn. Then he'll transfer it to the liquid oxygen and the energy will be rapidly released. Now remember, this energy released is the amount of energy that your body must burn off after consuming just a single bite of donut. Let's see how much energy that is. Clearly, the energy content of a donut, even this small bite, is very substantial. We're in the demo lab with Lonnie, where he's going to produce a phosphorus oxide from pure oxygen and pure phosphorus. The pure oxygen will come from liquid oxygen, which he's pouring into this flask. That will drive out all the air and leave an atmosphere of pure oxygen inside the flask. He also has a piece of solid phosphorus attached to the end of a string that he can lower into the bottom of the flask. Now this flask contains oxygen and phosphorus exclusively, and they're going to react. The question is, will the phosphorus be used up first and have oxygen left behind? That is, will phosphorus limit the reaction? Or will the oxygen be used up first and there'll be phosphorus left behind where oxygen limits the reaction? Oxygen can be the limiting reagent because when it's used up, the reaction has to stop. Or phosphorus could be the limiting reagent. When it's used up, the reaction has to stop. Lonnie's waiting for all the oxygen to evaporate, and when it does, he'll warm an iron rod and touch the phosphorus to initiate the reaction. Looks like he's ready to do that. Here's a warm iron rod that he'll touch to the solid phosphorus. When he initiates the reaction, you'll see a tremendous amount of energy released as the phosphorus oxide is formed, and the energy is released in the form of bright light, tens of kilowatts of light, the equivalent of hundreds of 100-watt light bulbs. Lonnie can use the light actually to read from one of his ancient tomes. Now, Lonnie's told me that the ink in some of these ancient tomes is only visible under the light from the phosphorus oxide reaction. I don't know if I believe that, but I can see that he can clearly read from the light from the phosphorus oxide reaction, the reaction of phosphorus and oxygen to form phosphorus oxide. We've asked Lonnie to demonstrate the formation of iron oxide, or rust. But rather than just sitting around and waiting for rust to form on iron, Lonnie's going to do it the rapid way. He's going to react iron and oxygen. Iron in the form of iron wool, and oxygen in the form of liquid oxygen. So here's his liquid oxygen, the beautiful blue liquid. And he'll ignite a piece of iron wool and drop it into the liquid oxygen. Now we know this reaction is very exothermic. It releases energy as iron oxide is formed. There's the release of energy that even breaks the beaker. Let's watch that again in slow motion. There's perhaps the most dramatic formation of rust you'll ever observe. The root mean squared velocity of bromine gas at room temperature can be calculated at around 200 meters per second. Lonnie can demonstrate that by allowing bromine gas to race down this raceway that he's produced. First, he'll fill one end of the flask with gaseous bromine, open a valve, and let it race to the other end of the flask. Here's one flask filled with bromine. Now watch carefully, this will happen fast as he opens up the valve and bromine races to the other flask. At 200 meters per second. We're in the demo lab with Lonnie, and we've asked him to demonstrate the inverse proportionality between pressure and volume. If you decrease pressure, volume would increase. Lonnie's chose to use marshmallows, which have hundreds of tiny air pockets of fixed volume. He's placing them in a flask where he can remove the air and reduce the pressure. As the pressure reduces, the volume of the air pockets in the marshmallows should increase. So let's apply a vacuum to marshmallows. And indeed, the volume of the marshmallows increase. In fact, they increase so much that the air pockets actually burst. Now, if we return the marshmallows to atmospheric pressure, the volume decreases dramatically, mainly because those air pockets burst. But apparently, bursting air pockets has no effect on the flavor of a marshmallow. We're in the demo lab with Lonnie, and we've asked him to form a sophisticated experiment where he forms a covalent bond, hydrogen chloride, from hydrogen in its standard state, H2 gas, and chlorine in its standard state, Cl2 gas. In order to do that, he'll first purge this cylinder to remove the air, and he'll purge it with nitrogen. Nitrogen is inert in this chemical reaction. It just serves to remove the oxygen and other gases from the flask. So here he'll purge the flask by allowing that nitrogen to flow through. And now we have a cylinder of mainly inert nitrogen gas. Now he'll add chlorine gas, Cl2, and Cl2 is a slightly yellow-colored gas. He'll bubble that into the cylinder and then add an approximately equal volume of hydrogen gas, H2. The H2 is in the red cylinder, and as he prepares to add that, let me tell you that the chlorine-chlorine bond, Cl2, the homonuclear diatomic bond, is a relatively weak bond. Cl2 bonds have about 250 kilojoules per mole. Now, that bond is susceptible to being broken by photons in the blue region of the visible spectrum. So if we were to shine a blue laser on chlorine gas, the chlorine gas would break down into chlorine atoms. And chlorine atoms are very reactive. So they'll react with whatever in solution, and in this case, it's a gaseous solution of hydrogen molecules. So a chlorine atom reacting with a hydrogen molecule will form HCl and release a hydrogen atom. The hydrogen atom can react with a chlorine molecule and release more chlorine atoms. So the reaction will proceed in a rapid chain reaction, releasing energy and producing a rapid chemical reaction. Here Lonnie will demonstrate the blue laser. It's hitting a screen now. When he removes that screen, the blue laser will strike the chlorine system and the chain reaction will begin. There's the formation of HCl from chlorine and hydrogen gas. For this experiment, Lonnie's taken solid copper metal in the form of copper wire and formed it into the shape of a tree. To this, he's adding silver nitrate solution. So we have silver ions in the presence of copper metal. Now, the reduction of silver ions to silver metal is higher on the reduction potential scale than copper ions to copper metal. So what we expect is the silver ions will be reduced while the copper metal will be oxidized to form copper ions. We'll expect silver to remove electrons from solid copper, forming copper ions, while simultaneously forming solid silver in this solution. The reaction actually takes quite a while, so Lonnie will seal it up and will do a time-lapse photography over the course of about 8 hours to watch the silver metal form. And there it is, silver metal forming on the structure of the copper tree, while copper ions turn the solution blue. So you see beautiful silver metal reduced from the silver ions being formed, and copper ions with their blue color forming in solution. We're in the demo lab to see Lonnie oxidize copper metal, oxidation state 0, to copper ions, oxidation state +2. The oxidizing agent will be nitric acid, NO3-. NO3- will be reduced to NO2. NO2 is a brown gas you'll see immediately start to form when the nitric acid comes in contact with the copper metal. Now, copper ions, Cu+2, are blue, so Lonnie can add some water to this mixture and we'll see the lovely blue color of the copper ions and the brown gas, NO2, formed above them in this oxidation-reduction reaction. We can demonstrate buffer capacity with these three solutions. The solution on the right is buffered, the center is basic and unbuffered, and the third is neutral and unbuffered. As we add dry ice, carbonic acid will form. But notice the solution on the right doesn't change in pH, while the solutions on the left rapidly change in pH, as we can tell by their color change. So, buffers resist change in pH. We've asked Lonnie to demonstrate the formation of an ionic bond. In this case, the bond between sodium and chlorine in sodium chloride. So Lonnie's filled a beaker with elemental chlorine. That's chlorine gas, Cl2. It's a yellow gas. He'll also use solid sodium metal. Solid sodium metal is a shiny silver metal that's very soft. He can actually cut it with a knife. Sodium metal is very reactive. It will react in air and water, so it's stored under hexane. He'll pull off a small chunk and immediately store it under hexane while he prepares the rest of the experiment. Now, to get the reaction to go, he'll want to clean the sodium, make the surface very clean, and warm it slightly to help the reaction proceed. He'll do that by placing the sodium in a spatula and then warming it over a flame to clean the surface and to get the sodium warm enough to initiate the chemical reaction. Now, the reaction between sodium metal and chlorine gas proceeds, but we know the ionization energy of sodium is greater than the energy released, the electron affinity, when chlorine accepts electrons. So the reaction goes because the positive ions formed on sodium and the negative ions formed on chlorine are drawn together, a Coulombic interaction, to form an ionic bond. The formation of that ionic bond, plus and minus charges attracted together, releases energy, and that's the driving force for this chemical reaction. And you can see that it's exothermic. Energy's being released. Bright red glow, typical of emissions from sodium. Now, the reaction between sodium and chlorine, of course, forms sodium chloride. We typically know that as table salt. And Lonnie's prepared some in advance. He has white table salt, purified, that he can show us. There it is, purified in advance from Lonnie Laboratories. And Lonnie tells me the salt that he makes in Lonnie Laboratories is far superior to any salt that you can buy in the store. So what does he have to do now? Lonnie's going to demonstrate, clearly hasn't had his breakfast this morning, that Lonnie Lab salt far superior to any salt you could buy in the store. Thank you, Lonnie, for that demonstration that sodium chloride, an important spice and food flavoring. And when you make it yourself, the satisfaction is so much more complete. We're in the lab with Lonnie to look at the reaction of alkali metals with water. Alkali metals react with water by ionizing, losing an electron. Those electrons that are lost are accepted by water, and the water releases hydrogen gas. Hydrogen is reduced. The reduction of hydrogen to form hydrogen gas releases energy, while the ionization of the metal, as we know, absorbs energy. In this case, you can see the reaction of lithium with water is relatively mild. That means the release of energy in the reduction and the absorption of energy in the ionization are about the same magnitude. Now we can also look at other metals. Sodium metal, for instance, one step down the periodic table from lithium, has a lower ionization energy. So less energy will be absorbed in this case, but the reduction of hydrogen on water to form hydrogen gas releases the same amount. So absorbing less, but releasing about the same amount means overall more energy is released. And indeed you see a slightly more vigorous reaction for sodium metal with water. Now, what about potassium? That's even lower ionization energy, and we expect more energy to be released overall. Here's potassium metal. Here it is in slow motion. You can see a very vigorous reaction with potassium metal. That's because potassium, the lowest ionization energy so far in our series, requires the least amount of energy to ionize, but again, that same amount of energy is being released when water is reduced to hydrogen gas. Now here's rubidium metal. And you can see rubidium, which has the lowest ionization energy, releases the most energy in the sequence. We're in the demo lab with Lonnie, and he's going to demonstrate the condensation of a gas, in this case water vapor or steam. He's producing water vapor on this hot plate in these soda cans. When a gas condenses, the volume decreases by several orders of magnitude. Let's see what happens when there's a rapid condensation as Lonnie plunges this into an ice bath. Let's watch again as Lonnie rapidly condenses a gas. You can see that the cans are crushed. That's because the volume inside the can decreases, reducing its pressure, allowing the external pressure to crush the can. Now let's look at the condensation of a gas into the liquid phase on a larger scale. Lonnie has prepared water vapor, a gas, inside a sealed container. As he plunges it into ice, that gas will condense to the liquid form. The liquid form is lower volume that lowers the pressure inside the flask. Now, the lower pressure inside the flask means the higher pressure outside could crush the can. Let's see if that pressure differential is sufficient to crush this larger can. There's a small effect. And indeed, high pressure outside, low pressure inside leads to a crushed can. We're in the demo lab with Lonnie, where he's passing a stream of hydrogen gas over platinum metal. Notice the platinum metal heats up as the energy released from the reaction of hydrogen and oxygen forming water is catalyzed by the platinum metal. We're in the demo lab with Lonnie to actually see those three balloons. So here's a balloon filled with only hydrogen, a second balloon filled with only oxygen, and a third balloon filled with a mixture of hydrogen and oxygen. Lonnie could ignite the balloons with his long torch, and we can observe the intensity of the explosions. First, Lonnie will ignite the hydrogen-only balloon. You can see an explosion, but a relatively mild explosion, as the hydrogen reacts with oxygen in the atmosphere. Here's the oxygen-only balloon. Well, that balloon more or less just popped. No real explosion there. Now, the hydrogen-oxygen balloon, that's a very strong concussive explosion. We're in the demo lab with Lonnie, where he's going to mix cane sugar and sulfuric acid. So sugar is a carbon compound. Sulfuric acid is a strongly dehydrating agent, so it will remove water from the sugar. When you remove water from sugar, what's left behind is essentially just elemental carbon. So the mixture of sugar and sulfuric acid will produce black elemental carbon in a rather dramatic fashion. Let's watch as Lonnie mixes these two compounds. Here's the sulfuric acid being mixed with the sugar, forming a slurry. You can see the reaction beginning. Lonnie will add a little bit more sulfuric acid. And you can already see black carbon beginning to form. This reaction is fairly exothermic, so it will proceed with the expansion of the forming carbon to form a rapid expansion of a long snake of black carbon. Let's watch that happen. There we have the formation of elemental carbon by the dehydration of sugar with sulfuric acid. We're in the demo lab where Lonnie's prepared to demonstrate the solubility of ammonia gas in water. This flask that he's opening is full of ammonia gas, and he'll put it on the apparatus and seal it. Now what he's going to do is introduce just a few drops of water into that flask. And since the Henry's law constant for ammonia dissolving in water is over 10,000, ammonia will rapidly dissolve in that small amount of water. What's happening now is the ammonia pressure is decreasing rapidly as it dissolves in the liquid. That lowering of pressure allows the atmospheric pressure to force the water from the lower flask up into the upper flask in the form of a fountain. In fact, it's a dramatic representation of the free energy released in this chemical reaction, as the free energy release can lift about a kilogram of water almost a meter high from the lower flask to the upper flask of the fountain. The reaction of liquid water and gaseous oxygen to form hydrogen peroxide is endothermic and decrease in entropy. So that reaction doesn't occur at any temperature. Lonnie can't show us that, but he can show us the reverse, the catalytic decomposition of hydrogen peroxide by the addition of manganese oxide. That reaction is spontaneous at all temperatures. So we're in the demo lab with Lonnie, who's prepared iron oxide and aluminum together so we can see that reaction. Now, this reaction is actually the reaction that was responsible for the Hindenburg disaster. The German dirigible was painted with aluminum paint over an iron superstructure that had iron oxide rust on it. And the reaction between the two is what caused that dirigible to flame and melt. The iron actually melted. Let's see if we can see that happen in our experiment. Lonnie's going to start the reaction by igniting a magnesium fuse. So that bright white is magnesium. Now the thermite, the iron oxide and aluminum, is reacting, and you saw molten iron pour from the bottom. It happened quickly, so here's a slow motion replay. The reaction is beginning. Now, as the reaction takes place, watch the bottom of the crucible. Molten iron will pour from the bottom. Here it comes. So there's a chemical reaction that's so violently exothermic that the product is molten iron. Lonnie can come in and demonstrate that there's still a tremendous amount of heat being given off by that iron. Indeed, such a tremendous amount of heat that Lonnie can enjoy one of his favorite campfire favorites. We've asked Lonnie to demonstrate the burning of a towel under two different conditions: isopropanol pure and isopropanol water mixture. So first, isopropanol. He'll prepare some isopropanol in a beaker and a towel which he'll saturate with isopropanol that will burn. Now, the flash point of the paper that Lonnie's going to burn is over 500 degrees Celsius. So if that begins to burn, that means the flame is hotter than around 500 degrees Celsius. So he'll soak this piece of towel in the isopropanol and he'll ignite it with the torch in front of him. Let's see how hot the isopropanol only towel burns. You can hold it with a pair of tongs, keep it away from his body, and ignite it in his torch. Isopropanol is a flammable liquid, and you can see he has to hold that fairly far away from him. That's a hot flame, and you can see it's going to burn the towel. So the temperature of that flame clearly well above 500 degrees, the flash point of the paper, completely consuming that paper towel. Now what would happen if we added water to that isopropanol? An isopropanol water mixture, will that burn? Well, let's do the experiment. Here's Lonnie going to make a 50-50 mixture approximately of isopropanol water and burn that in a saturated towel. So he has half his towel left over. Puts that in his isopropanol water mixture, and let's ignite that with a torch. Now we should see, will this towel reach 500 degrees and combust? Well, you can see already Lonnie can hold this one very close to himself. It turns out that's not a very hot flame. And it's not a hot flame because the water is actually evaporating, and it takes about 40 kilojoules per mole to evaporate water. That carries heat away from the flame. And you can see Lonnie can handle the towel right after the flame goes out. It's hardly been warmed at all. So isopropanol water burns much cooler than isopropanol.